Business Solar Breakfast. Today we are opening Cassini Big Ideas campaign. Let me share a few words about Cassini Hackathon. Europe-wide Cassini hackathons are the major opportunity to develop ideas for digital applicants of space data. They are particularly addressed to students, graduates, researchers, and startups. Each hackathon takes place simultaneously in 10 Europe cities, and the local organizer offer everything needed to form a great team, learn about access space data, identify customer needs, and start working on digital solutions. So, ZICER is the organizer of a Cassini Croatia edition, and Cassini Hackathon will take place from March 24th to 26th. Before the hackathon, we are running the Big Ideas campaign. This two-week event is the perfect opportunity to gain some valuable insights and hone your skills. So, before we start today, I would like to ask our CEO, Frane Šesnić, to share a few words with us.
Good morning, everyone. Thanks, Thomas and René Michel, for coming from all over the Luxembourg to share some expertise with us this morning in order to boost our, let's say, ideas into space. Also, I would like to welcome our friends from TIS, Carlo. Good morning, and I hope this will be a very fruitful morning for all of us, and that we will learn a lot about possibilities in the space technology. So, welcome to ZICER. ZICER is, like we always said, the biggest startup hub in Croatia, and I hope it will be a good playground for new ideas, and let's see what will everything that we do today will bring to us in the next few weeks. Thank you very much.
Thank you, Frane. As Frane said, today we have a special guests, our sponsors and partners from SES Techom, who came from Luxembourg to be with us today. So with us are René Michel and Thomas Böhmer, who will tell us more about SES Techom. So first we will hear more about SES Techom from Thomas, who will also share with us some words about space-based quantum key distribution. Thomas, the floor is yours.
Perfect. Hello, everybody. My name is Thomas Böhmer. I was a system engineer actually until 28th of February at SES, and now I'm a business development manager, so I'm exactly here at the right place for explaining you what we are doing. I worked on optical communication. I started 9 years ago working on optical communication with satellites, and we moved from optical communication to encryption systems, and in the end we go to quantum key distribution systems, which are based on optics. Before we start, I will, or here a little overview, I will provide you a very quick introduction into who is SES, or SES as we call it. Then the next agenda point will be why we do this, a little bit background, why we're actually doing space quantum key distribution. I will present you Eagle 1, which is one of our largest projects at the moment. And then I will provide you some food for thoughts, what we think could be interesting challenges or problems to address during the hackathon. So let's start. SES. So everybody here knows SES. Actually, you've been in contact passively with SES. So, for example, we started in 1984 with the linear television with geostationary satellites. So, whenever you watch the Champions League, FIFA World Cup, or maybe if you're not interested in football and you watch the NHL, then this is distributed via our channels. We have over 2,000 employees worldwide. We have over 70 satellites in over 20 locations, and it's I like it very much because it's also a very diverse place. So we have over 70 nationalities working in our offices, and actually also a lot of from Croatia, just to mention that. SCS was always very innovative. So first of all, we, for example, have been the first commercial satellite operator which used electrical propulsion satellite in space. We've been also the first commercial satellite operator who used reusable rockets. Everybody knows them from SpaceX nowadays. We are going digital, but what we mean by going digital is basically we go digital on the payload, which is the more tricky part, because usually you would like to keep the complexity in the satellite as low as possible. And what we are also doing since now already 6 years, we are looking very heavily. We have a lot of projects in quantum key distribution, both actually terrestrial and also on the space side. So why quantum key distribution and why space-based quantum key distribution? So in order to understand that, we have to go one step back for cybersecurity. So in cybersecurity, one of the main pillars, which all other cybersecurities topics basically or subjects are somehow interwoven with, is encryption. So just to state a few facts at the moment, some current, how the current status is. So encryption, we are using basically 2 encryption schemes today. You can class them into 2 different categories. And I guess a lot of you know, so we have symmetric encryption schemes, and we have asymmetric encryption schemes, which are also known as public key distribution schemes. And we are all based on mathematical complexity, or computational complexity, and it's all based on the assumptions that certain problems are hard to solve. And we always have to update this. Because either the crypto analysts are having new good ideas how we could attack one of our algorithms, or the computer performance is increasing, and due to that we have to increase our key length again. So this is always this kind of game which is going on since years, and yeah. And what was very important, a very important step also that the internet looks like it is today, is basically that this asymmetric encryption was invented, where you have, so for the symmetric encryption you have only one key, and both parties share the same key. And the asymmetric encryption you have basically 2 keys, and this was solving the big problem of how to distribute the keys. Because the key distribution is the critical part. Once you have this done, you can go to the symmetric encryption, and which is, let's say, more straightforward, and the assumptions are not so hard like for the asymmetric part. So I guess a lot of you know, we heard already from RSA or Diffie-Hellman, these are the classical asymmetric approaches which you use every day for every time you open an HTTPS website, an SSL connection, or plenty of TLS connections. You always use this kind of encryption scheme. If you do a bank transfer, doesn't matter actually. This is always included either for encryption or for digital signature or authentication. So the problem is now, or this is also status, we have a new thing coming, and this new thing is called the quantum computer. So there are ongoing developments on the quantum computer, heavy investments. Basically, Europe was leading the game, maybe it's still leading the game. The European Commission is spending a lot of money in these research activities. But just to give you an idea alone, IBM announced just, I think in October it was, that we will invest another 30 billion euro in the research of a quantum computer. We're also in contact with Google Labs, which have an own quantum department. Microsoft has their own one. Actually, all of them. You name them. Amazon has their own one. We are all working heavily on this, and we expect that this will be the next big game changer. And the reason why we all invest in this is because I mean, if you go for the classical computer, you can always put more transistors on your chip, and that's why you can roughly expect that you every 18 months you can double your performance. But unfortunately now we are already getting so small that you have problems to put more transistors on a chip because you have some interference with quantum effects. So in order to avoid this kind of quantum effects, you simply jump the line and then you go directly to the quantum computer. And with these computers are working very differently. So they really are a quantum system. So we are not using bits like with 0 and 1s like we do, but we use superposition. So you have always 0 and 1 at the same time. And just to make another example or an idea how it's differently, so in the end, it's not a logical, it's logical, but it's not a deterministic system. It's a probabilistic system. So your solution, which you will derive out of a quantum computer, will always be a probability attached to the solution. So it's not, I mean, this is why you have to calculate things many times, and you only can get a very good probability that this solution will work. The problem is they are very powerful, these kind of quantum computers. We are far more powerful than parallel computing or something like that. And again, why companies are so heavily investing in it, the nice thing is, for example, for truck research, so if you want to invent new trucks, you really can simulate this quantum system with a quantum system and not modeling it in a, let's say, non-quantum system, a quantum system. So this is bringing huge advantages. So a lot of research institutes or pharmacy companies are also investing a lot of money and are very interested in these developments. Because we are so powerful, there are already algorithms known today since the 80s actually. We have a problem that, or not a problem, we are capable to break basically all the hard problems which we assume for the asymmetric encryption. And therefore all of these public key infrastructure, basically encryption schemes, we are prone to fail. And this will happen. I mean, this is coming as soon as we have this, we call it quantum relevant, so cryptographic relevant quantum computer. So the acknowledged working hypothesis right now is that in early 2030s, a powerful quantum computer exists that can break common cryptography methods such as RSA 2048. So, I mean, this working hypothesis was also the reason why, for example, NIST, which is the National Standardization Agency in the US, we started to standardize certain solutions. But it's also the reason why, for example, the US government just last year announced a directive, actually the White House announced a directive that all government agencies have to start the transition to quantum safe cryptography. And we even have a roadmap published. So this is really real. This is not something which is far in the future. We are really have to be careful there. So, yeah, as I already mentioned, so the direct implication is that critical to develop quantum resistant methods. So this is something which has to happen. And yeah, transfer them into practice, which is really difficult because in cryptography, everything what you don't want is innovation or something new. Because you only trust in systems. I mean, you build trust over time, and this is the critical part. The best thing is you have something which didn't change for 30 years. And you know exactly how it behaves. This is what you would like to have in cryptography. You don't want to have some super duper new scheme. Unfortunately, this is not working anymore because there's this threat. Yeah, then there's an additional threat which is also working, I mean, existing already today, where you have to act today basically, And this is, I mean, if you have sensitive data as a government, for example, and you would like to keep your data safe also in 30 years, I mean, there are programs you can you can go on Wikipedia just as an example. There are plenty of programs, but the US is, for example, running the Bull program, it's called, where it's just simply trying to capture as much internet traffic as possible, and we store it. And we store it, and then we can decrypt as soon as we're capable to decrypt it. So the point is, you could already store critical data today, and once you are capable to decrypt it, you do it. So if something is relevant for you and has to remain secure, this time, and you have in the time you have to think about how long it takes to migrate it to a quantum safe algorithm, then if this time is bigger than the availability of the quantum computer, I mean, it's not clear when it will come, but where already some existing, but the number of qubits is still too low at the moment. But as soon as this happens, then you have an urgent need to act, basically today. And yeah, the switch to quantum resistant processes will ultimately require migration of large parts of your infrastructure. So it actually doesn't matter what kind of solution you choose, because I will just show two potential solutions. It's clear that you will have an impact on your infrastructure, and it's unfortunately not coming for free. So, what are the two approaches? So the two most common approaches right now, and you could come up with a new one, obviously. One we call post-quantum cryptography or quantum-resistant algorithms, and the other one we call quantum key distribution. So let's talk about post-quantum cryptography. So basically we do exactly the same as we have done before. So we try, I mean, our complex problems are not working anymore, so we try to make them even more complex. So we go for lattice-based systems, for example, but this comes with a lot of challenges. First of all, what I already mentioned, you have a problem as before. You cannot really trust this because you don't have really experience. I mean, you come up with a new mathematical system and you claim it's very complex, and it's true that it is very complex, but you don't understand. It's so complex that you do not really understand it completely. So maybe there are some open site attacks which you don't know, side channel attacks, and it could be broken if somebody comes around with a better algorithm, also with a better quantum computer algorithm, for example. The next problem is that these kind of algorithms or implementations where you need a much more efficient hardware and software implementation. So usually your key size is much more, it's increasing dramatically. I mean, we talk now, for example, if you talk for RSA 2048, obviously you have 2048 bits, but in quantum resistant algorithms, you go into megabits of key size. And because this is so complex, your standard computer has a problem to calculate or to resolve these kind of equations, which is an additional problem. And then it's depending on the use case. I mean, if you go for an IoT device which has very low CPU power, then probably it doesn't even work. And then, and this is one of the biggest problems, actually it turns out to be one of the biggest challenges, you really have a problem with the adaptation of the network protocol. So because whatever kind of protocol you take, like it is designed today, this was not foreseen. So the size for the header of the cryptographic key is way too small. So you're not able to put in a megabit or kilobit, I mean several kilobits cryptographic key of that size. This is simply not possible. So what you have to do is basically you have to change your protocol. You have to change very basic protocols on the internet, like TLS protocol, like IKE, which you use for VPN. Like even more. I mean, there are plenty of protocols where all not really suitable for using this kind of algorithms. I mean, it's not really, there are also algorithms you can use, but then you have other advantages. It's always a trade-off. So there's a second option which you can do, and this is basically exactly what we are going to do. This is quantum key distribution. So the security on quantum key distribution is basically is based on the assumption that quantum physics or quantum mechanics, that the theory of quantum mechanics is correct and complete. So that nobody comes within 20 years with an even better understanding of quantum mechanics and can still leak it. But even if the quantum mechanics system or quantum mechanics as we understand it today wouldn't be complete, basically our security only relies on two things, and one is basically the Heisenberg uncertainty principle, and the second point is the non-cloning theory, that you cannot clone a quantum state. We have security proofs which are shown, if you only assume these two, you can still guarantee the security of a quantum key distribution protocol. Then obviously you need some authentication, because once I talk to another party, we have to authenticate each other, which has to happen outside of this channel. And okay, this is actually applicable for both, also for the PQC approach. Obviously we need a trustworthy implementation, otherwise it doesn't work. But the reason why I write it here as an extra bullet point is, I mean, in the history or in the past or up to now actually, we always use this mathematical complexity, and we have the impression that we can control this mathematical environment and we understand it. And in the quantum key distribution, here comes the additional challenge, where we really have to implement the physical world into our security proof, which is not really working. And this is an additional challenge to understand how do you really implement it on a physical level so that you are not able to eavesdrop some information. So yeah, and that's already comes to the challenges. I mean, the security criteria and proofs and the side channel attacks are new, because now you can also come really with physical side channel attacks, like pointing a laser into your receiver, and maybe you get some side information, and due to that you could calculate some information on the key which was exchanged. There have been also side channel attacks already of this kind, but usually we're more easy to counteract with some additional filter, for example. And then you have the network aspect. So QKD, as it is today, is a strictly point-to-point technology. So you only communicate to your next server or to your next QKD device. And this comes with a little challenge because we are using usually photons or optical communication for these QKD receivers or QKD key exchange. And because the fibers are adding attenuation to your link budget, you can only go for, I mean, this now depends, but let's say roughly 100 kilometers in distance. And then if you want to go further, so if you want to go from Zagreb to Brussels, you need certain hops, and this is what we call trusted nodes in the concept, which is not so well received in particular in the governmental world, because like everybody else, they prefer much more end-to-end security, so we don't want to have any trusted node in between. But on the commercial world, we have something like that already, because usually this kind of, I mean, how the cloud storages and so are built up, we basically do exactly the same. You have always this kind of region, and you do your backups. So you could use this kind of system also for banking on the commercial world. Okay, so the limited distance, as I said, is one of the big problems, and that you have to introduce these trusted nodes. So this is exactly the reason why we go for Eagle One. So Eagle One is our biggest project right now. It started last year, and it's a quantum key distribution satellite. So what we do with Eagle One is basically the satellite itself becomes a trusted node. And the satellite is flying in a LEO orbit, so it's a low Earth orbit from the pole to pole, and it can see every point on the Earth. So you have now two advantages. First of all, you can dramatically reduce the number of trusted nodes which you require for long distance communication, because you only need one, which is the satellite, which has some special attributes, because once the satellite is in space, it's not really easy to access. And the second one is you can go for long distance communication, which is not really possible if you go on a terrestrial network. In particular, maybe you can do it in Europe, but you could never go from Europe to the US, because then you would need every 100 kilometers basically a trusted node. So in Eagle 1, just to explain the system quickly, I mean, on the left-hand side you see the position 1, which is probably communicating to Madrid, I would say. And they both share one secret. So the satellite and the ground station share one secret. And then the satellite is flying to position 2, which is maybe Göteborg. And the satellite and Göteborg, again, are sharing one secret. And because the satellite is flying around all the time, so every time he sees a ground station, he's sharing a secret with the ground station, which is below. So if now Göteborg and Madrid are deciding they would like to communicate to each other, they will inform the satellite operation, or actually the payload operation center, and then the satellite will, I mean, this is now oversimplified, I have to admit, but they will basically XOR the key, so we will combine the key of the both of a shared secret we have with Madrid and a shared secret with Göteborg, and we will send it down. And we can do it even over a public channel, doesn't matter, RF channel or whatever, everybody can read that and can know this message because it's anyhow encrypted. And you will send it to one of the stations, let's say to Madrid, and Madrid already knows which promise or which secret it is sharing with the satellite, so it can decrypt the message, so it knows then exactly what kind of secret the satellite was sharing with Göteborg, and it can use this kind of key for encrypting the data we want to exchange. And on top of that, I mean, all of these regional areas, because you will also distribute, for example, in a city like Zagreb, you will probably only have 1 or 2 ground stations, and then you will also distribute terrestrial. So then you have this kind of trusted nodes again, but again you can dramatically drop the number of nodes, plus you could also communicate with Australia, which wouldn't be possible otherwise. And then I would already come, let's see, time-wise I'm good, food for thoughts for the hackathon. Except you already have now a question. If this was this halfway clear? Food for thoughts. So you're already thinking in the correct direction. Okay, Eagle 1 is an in-orbit demonstration, so it's funded by the European Commission and ESA and the national different nations of Europe. I mean, you can read it here. It's Germany, Luxembourg, Austria, Italy, the Netherlands, Switzerland, Belgium, and the Czech Republic. And because it's an IOD or IOV, in-orbit demonstration and orbit validation, this is only one satellite for now, so because we have to prove that this technology works. But if you really go for commercial service or an application for governmental use, this is a constellation. You can even, and then you can go crazy. You can go for a constellation. Actually, you can even miniaturize the satellite, and you can go just for a constellation. I mean, depending on the needs of a customer, that he gets basically his own constellation. I mean, if you take huge cloud providers, for them it might be interesting to just fly their own constellation, or huge insurance companies or something like that. or you share the asset. But in the end, yes, it's for sure a constellation. I mean, in the end, depending on the amount of key you would like to exchange. Yeah, and then we come to the foods for thoughts for the hackathon. So I would like to provide you 2 ideas, or 3. I mean, this is, one is always the use case. So as I already mentioned, the tricky part is with the protocols. So because all the protocols have not been foreseen for these quantum resistant algorithms, but it's much easier to inject the quantum key, which is basically perfect entropy, into these kind of protocols. So you could come up with your own use case, whatever you want. I mean, the classical ones are basically, for example, backbone encryption between 2 data centers. And there's also one official ETSI specification already published, as you can see, since 3 years, which is a protocol data format for REST-based key delivery API. And then you could mock up your own QKD system. I mean, this doesn't have to be very sophisticated. It could be done with a simple database, which is basically owning some random keys. And then with that, you access via this API, this kind of database, you get your key, and then you inject your key in whatever kind of application you would like to inject it. I mean, it can be in a protocol, can be IPsec, can be MACsec, can be layer-based, can be even in a smartphone application. I mean, there are plenty of ideas. This is basically an open space to explore for you. And the second food for thoughts slide, these are basically optimization problems. So obviously the quantum link is in the end, because we're using photons, it's an optical link. So you have to have a line of sight. I mean, optical links are very prone to atmospheric effects, but then we are getting this, it's getting too complicated. So keep it very simple. The first thing what you need is a line of sight. I mean, if I don't see each other, if I'm not able to see you, obviously we don't have any option to send photons. So the idea here would be basically the development of a satellite orbit simulator, but you could also take satellite orbit simulators which are already online. There are several actually programs doing this already or providing this kind of service. And then combine it with an existing public cloud database, but you could also use Copernicus data, and yeah, basically generate the various line of sight statistics. So from the satellite to the site on different locations on the Earth. And I mean, depending on the data set you use, like if you use the Copernicus data set, this is really huge, so maybe you just limited to Europe or to other regions which you prefer, but this is one option. If you think, I mean, this is in the end an optimization problem. Here you can do a lot of things, because if you think this is too easy, you can even extend it. So once you have this kind of link availability, you can exactly calculate the sizing of a satellite constellation, which is providing quantum key distribution. And here, yeah, this is then depending on, obviously, what is the key rate the satellite is providing, or the key quantum key quantity, how often do you see the satellite, how big is your fleet, how many satellites do you have, what is your traffic matrix between the different sites. Yeah, and how can you make sure that a certain number or minimum number of quantum keys is provided to the various locations. And I mean, we are also doing something like this. These are actually real problems, in particular the last one we are working on. Yeah, and here you have plenty of options for your personal fun. I mean, you can use machine learning, generic algorithms. We tried several approaches, and it's not obvious. It's an interesting problem, actually. And with that, yeah, I'm already through my presentation. And if you have additional questions, or if you have any questions, please shoot. Please. That's true. I mean, if you think now in the direction of SCADA, for example, as an industrial. Yes. Yeah. Yeah. I mean, this is the idea. I mean, the idea also from a European Commission is basically, obviously, to protect sensitive governmental data for their own purposes, but it's also basically securing critical infrastructure. So there are plans to use it, for example, in SCADA networks. I mean, we all know the security level of SCADA networks was basically not the design parameter as we started to design it, so it's extremely low, but it's nowadays considered as a huge problem. And we also have to admit, maybe I can reveal this as well, because if I show this slide, it looks a little bit like either or. So it's either you go for quantum resistant algorithms or PQC, or you go for the QKD. But that's not true. And the reality is basically based on all this experience, how it is today, we won't like to go. That's actually very clear. We will go for a so-called crypto-agile approach. So we will combine. So depending on the level of security, you will combine both technologies. So if one technology turns out, because there's, for example, some algorithmic improvement, and your PQC algorithm isn't working anymore or has some flaw, then your security can still rely on the QKD system and vice versa. So basically, this is the way to go for all systems nowadays. So in the best case you would like to use today, the best thing you can implement is to implement a classical, a PQC and a QKD system, at least one algorithm or one primitive out of each category, and you combine them. The trick is the combination, which is not so straightforward. You need some, I mean, this is a research topic actually. This is really critical, because if you do it wrong, you even reduce your overall security level. But if you combine them, and you also need the classical today, because as I said, this is the only one we have the most experience with, so we trust in that one still the most right now, even if we know that this is vulnerable. But yeah, today the cryptographic communities, we don't, I mean, we like it, but we don't trust it because there's no real experience up to now. I mean, on a few quantum resistant algorithms were already 20, 30 years around. So there's some kind of trust, but as I already mentioned, we have other disadvantages, like we are super CPU intensive, which you can never run on your mobile phone or on a server, because then most of the time your machine is only busy with encrypting and decrypting, and you cannot use it for normal browsing anymore. Did I answer your question? Okay. Any other question? I mean, if you would like to know more or you would like to discuss this deeper also, I mean, in terms of what might be real key rate or quantum key quantity, yeah, please, you can reach out to us and we can define that a little bit more concrete if you want. Thank you very much.
Thank you, Thomas. And now I would like to ask René Michel to talk about, just to switch, to talk about maritime security and surveillance.
You can just share your Hello, can you hear me? All the way back? More or less? No. If I speak lower, it's better. It's better, okay. So my name is René Michel. I'm coming from Bolivia. Who knows where Bolivia is? Good. So are we still alive? Are we still awake? Yes? Yes, we are. Okay, cool. I live in Luxembourg. Bolivia and Luxembourg, you know, they have a lot of things similar in common. We don't have a sea. But anyway, I work and I support a project for EMSA, which is the European Maritime Safety. Okay, you have to complete it. Let's try again, okay? Luxembourg, Bolivia, we don't have a sea, but nevertheless, I work supporting a project for EMSA. EMSA is European Maritime Safety Agency. There we go. I forgot the clicker. So I'm going to be talking about a REACH platform, which is a GovSatcom platform, a satellite platform that SES has. I'm going to be talking about what are the EMSA, as we call it, the needs. And then I'm going to describe the solution. And while I'll do that, I will ask constantly. So I'll expect you to answer things. Yes, no, yeah, you know, whatever, da, whichever word comes to you. If the question is not clear, if something is not clear, do not hesitate to ask me to repeat, to go slowly. You know that there is this amazing word that you have, pomalo. You can say that. But since I am coming from Bolivia and speak Spanish, you have to say it in Spanish. No? Despacito. So you go like this. There we go. Let's start. We are in the mood now. Now you're awake. So I'm going to describe the REACH GovSat platform. The REACH platform, who knows what a satellite platform is? Who knows what a satellite is? Who knows what a hub is? Because otherwise, it's a bunch of words that we don't understand. So, who knows what a Wi-Fi router is? You know what it is? So let's imagine I have a house, and I have the fiber optic that comes to my house, and then I have 3 floors, because I have 3 kids, 3 different wives, you know, 3 different nationalities, you know, something very practical nowadays. And I need to provide internet to all of them, but I don't want to do the cabling. So what do? I put a router, Wi-Fi, and a couple of repeaters, right? So the satellite is pretty much the same. It's something that's on the sky. We send a signal, and the signal is repeated to all the countries. Okay, all the coverage that we are covering. We have a footprint, just like a flashlight, that is covering. Okay, that's the satellite, the main concept of a satellite communication, of a communication satellite. Sorry, and then you need a platform. You need to take the data, the IP data, or the broadcast TV or whatever, and transform it, modulate it into a signal that goes to the satellite, and then it comes back. Okay, so that's the satellite platform. In this case, REACH is a platform that was developed for governments and for communications for governments in Europe. The idea is that you can use multiple satellites. You can request the service on demand. The European Commission will book a satellite capacity, a set of frequencies, and they will be using that on demand based on different projects. That's REACH. We can have symmetrical link. You know what a symmetrical link is? What's a symmetrical link? It's when you upload and download at the same speed. You can also have asymmetrical link, right? It's most of the time what in homes we have, because we're not uploading information all the time. So REACH started last year, and one of our first customers is EMSA. We are providing capacity, satellite symmetrical links to EMSA. You remember what EMSA is, right? So I'm going to explain what are the needs from EMSA, and I have some bullet points there. I'm not going to be reading them. I trust that everybody who's going to the hackathon knows how to read, so you can read that. But I'm going to explain. EMSA is supposed to provide some kind of connectivity and support the member states to provide safety. In this case, safety and security is not as encryption, but in the sense of we need to have safety and protected borders on the sea. From piracy, illegal fishery, or people going from one country to another country without the proper authorization, like from the north of Africa all the way to France, okay? And EMSA provides support to member states. Member states can request, can we have this particular solution to monitor our seas because this is our situation, this is our use case, blah, 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 blah. And EMSA evaluates that and provides the service. EMSA is an agency, it's a European agency. That means that it utilizes the industry from Europe. In this case, it utilizes SES to provide this service. So it means that they need to provide satellite connectivity, they need to provide drones that are flying, taking videos to do the controlling, the patrolling. They need to provide a crew that will do this monitoring to the member states. It could be the German police, the Romanian police, it could be Icelandic police, we have Portuguese, Spanish police that they requested this, and we install this solution in those vessels. We install them in the boats. They go we partner with the providers of the drones. We provide. I'm going to show exactly the solution, and we attend to the needs of EMSA. So far, is it clear what the problem is, what the need is? Because if we don't understand what is the need of the customer, doesn't matter which solution I'll tell you, you will be like, oh yeah, that's a cool solution. But if you don't understand what we are trying to solve, I can just tell you a short story. So I want to know if it is clear what are the needs. We need to provide satellite connectivity for vessels, for boats that are on high seas, that they are moving, and they are flying drones. These drones will be streaming video real time towards the police. They will go around in the Mediterranean or around Iceland looking for illegal fisheries, fly the drones, do the patrolling, and real time send the signal, send the video to the headquarters, and then if there is something, they will take action. So that's the use case. So it has to be near real time. We're talking about few seconds. We have up to 5 seconds of latency in our contract as latency for the video. So far, is it clear what we're doing? I see you all confused. Yes, no, more or less? Okay. Remember that you have to answer, eh? So these are the last 4 missions that we had. We had the land, the Sentinel that monitor, yes. In Croatia, we don't do the solution for Croatia with EMSA, but I think, yeah, you should have drones here, yeah. These are the missions that we had. So this was in use already in the Mediterranean, from Spain all the way to Pisa and to Crete. So that's close enough to the Adriatic. Then Thor and Freya, yes, those are the names of the vessels, Thor and Freya. They are in Iceland. They go around the fjords. We were supposed to have an Bailey Sentinel, but they changed the name to Ocean Sentinel, and I felt really disappointed. You go to your friends, and I monitor Baileys. But anyway, we still have Thor. So these are where we have the sites and the solutions. In Croatia, right now, we don't. We had Romania. We will have the German police. Yeah, so that's the closest. Any other question? So I'm going to describe our solution. this is our solution. It's blue and green, because we like those colors. Anybody can read and understand what we have in the solution? Let's see, we should have here, oh yes. Can you see the dot? Okay, so we have 3 components. The satellite link, the rich platform that I explained, remember? Yes, no, yeah, ne? Yeah. Dobro, okay. Then we have the service and operations based on SD1. Who knows what SD1 is? Don't worry, there's a slide for that. And managed Wi-Fi. These are the 3 components, the 3 pillars of the solution. So we have a geo antenna that's talking to a geosatellite. You know what a geosatellite is, right? It's a geostationary satellite that is basically like a mirror fixed from Earth that is matching Earth's rotation. We have this hub in Luxembourg. We upload the internet. It goes all the way to our vessel where we have the VSAT. We have the small components that I'm mentioning here because it's part of the SD1. The ACU, which is an antenna control unit that is making sure that the auto-pointing antenna is tracking the satellite, because although when you are on Earth, the satellite looks that it's not moving, if you move, you need to follow it. Is it clear? So we have an auto-pointing antenna, we have a modem, and then here we have a server that has the SD1 and the Wi-Fi controller. And also we have local ISP when it is parked, when it is in port, the vessel. We have a secondary internet access. I will explain why. And we have the end user that they have a switch and they have access points because they connect via Wi-Fi. So let's talk about the solution, the satellite link. This is the most basic part of what SDS does. This is basically the bread and butter of our business. We have a hub, as I said, in Luxembourg that is uploading the link to the satellite. We can work with multiple satellites. That means that we can do roaming. You know what that means for a satellite link. You know what roaming is. When you go to a different country, you can use a different blah, 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 blah with your phones, right? In these cases, if you are getting out of the coverage of the satellite, because there is no satellite that covers the whole planet, if you're getting out of the footprint of where the satellite is sending the signal, you can switch to the next satellite. So the antenna and the modem are registered and they know that you're going out, start looking for this frequency, start looking for this other satellite, and do a handover and just change to the satellite. That's part of the platform. We provide 10 megabit symmetrical over satellite to the vessels. And on site, we have a modem, an ACU, and antenna. So this is pretty standard. This is pretty standard. Any VSAT solution that you get in the market, you will get this. On top of that, we have an SD1. An SD1 means software-defined wide area network. Basically, it's a network that is defined through some orchestrator. You were asking before about VPNs. This is a set of VPNs that we deployed, and they are orchestrated and built dynamically based on our needs. What do we do with that? First of all, we have, let's go back here. Here, we have on the vessel, we have a branch. We have a server that acts as the VPN, as the SD1. So we have, every vessel has a firewall that we can configure. We can set the policies that we want. We can open, close ports, do whatever we want. So this is a firewall. We can put security, we can encrypt the data, we can do whatever we want from a security perspective. Now we're not talking anymore about safety from the EMSA perspective, but now we're talking about cybersecurity. We can block the traffic. We can decide what we want. We can build tunnels because we have an SD1 hub in Betzdorf. We can encrypt all the tunnel from all the vessels, all the way from Betzdorf, and from Betzdorf it goes to the internet. Or it could go directly from the satellite via the platform and encrypted to the internet. It's based on what they want. Because we have a tunnel that goes to Betzdorf that is encrypted, we can use that for management. As you remember, I said that we have a modem, we have an ACU, we have a server, we have managed Wi-Fi on the remote side. And we use these encrypted tunnels to manage them. If we need to change to a different satellite, if we need to change the configuration, if we need to access and see the traffic and encrypt it, we use this. And we provide this access also to the customer. They say we want to have visibility on the stats, and we will see later on the stats of the ACU, if it is going where it is supposed to go, where they are reporting that they are going. So we can do that in an encrypted manner using these VPNs and these orchestrators. It allows us also to create point-to-point or multi-point access to all the vessels. So if the customers tell us we have 5 vessels and we want to have a network for all of them, a private network that connects all the vessels, we can do that. Currently, the solution provides 2 SSIDs. Who knows what SSID is? Any idea? Sorry. Yeah. It's the name of the Wi-Fi. Yeah, we provide 2 Wi-Fis. The EMSA reporting and EMSA operations. The operation has a higher priority. It is defined for a UTP video because that's the protocol that they are using, and it's optimized for that. So our SD1 on the branch side on the vessel is giving priority to these packets because that's what the customer wants to transmit. And we have the reporting, which is in theory for them to prepare the report, have a Microsoft Teams and these calls and report what they've done. We can see the traffic. Usually it's for Netflix, but anyway, we don't blame them. They are on the sea for 3 months, so it's okay. They can use Netflix. But yeah, this is reporting. It's pretty interesting. In operation, you only see the traffic UDP and the public IPs that where we are destining the traffic. And in reporting, you see TikTok, Instagram. That's life. And then we have 4 LANs. We have a LAN for reporting and operations, so you can access to both networks via Wi-Fi and via LAN, with a cable. And we also have local and remote management. Okay, we are under attack, everybody under attack. So we have also and remote management. We have networks that allows the ACU, the modem, the server to talk to each other, and we just need to configure the modem and tell the modem you need to connect to this satellite. The modem will configure through this network everything else. And we access remotely to the modem. And of course, we have a local access in case something goes wrong and we need support, or when we are doing the implementation, when we go there, we can connect to the server and do some tricks and fix things that were broken. I wanted to go, yeah. So here you can see the solution. We have a geo, blah, 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 satellite, which is basically reach, sending the internet to the VSAT. We have the SD1 and everything. And you see this yellow line. Any idea why we have local ISP or a secondary internet access? Any idea why? We have a present for the right answer. Yeah, that's true. If you're close to the shore, yes. That is partially true. That's like 20% of the answer. We're missing the 80%. Redundancy for Netflix? Redundancy for Netflix, for TikTok. By the way, don't forget to subscribe after. No, I'm kidding. Management. We are not allowed to pass traffic via the local ISP or usually vessels, they have an internet, a satellite connectivity which is asymmetrical and it is 2 megabits. Yeah, that's the standard. And we're not allowed to pass traffic through that because we wouldn't charge for something that we're not providing. But in the contract we request an out-of-band link in case something happens, if this dies for X, Y, Z reasons, we need to troubleshoot because we send 2 servers, 2 modems, we send spares. And if something breaks, we need to access. We need some way to access. And the SD-WAN is able to manage and aggregate multiple internet accesses. So think about that. And the SD-WAN is able to handle multiple internet accesses. Think about that. I'm not giving the answer for the hackathon, but just think about that. Finally, the SD-WAN, the user experience. The user experience, what they see, they don't need to know that we have a server with SD-WAN. They don't need to know that we have all these policies. They don't need to know that we're giving priority to A, B, Z, blah, blah, blah. They don't need to know that. What they need to know is that they have high throughput internet access for their services, for what they want to stream, that they have as many SSID as they want. If suddenly they say we want to have EMSA Netflix because they are watching and we want to limit that to only 2 megabits, please, we can do that because every single data plane can be limited, can have its own policy. That's why they are isolated from the other ones. And we have stats. We can show different levels. How many users are connected to the Wi-Fi? We can see how many sites we have on the SD-WAN, what is the traffic that is going through the SD-WAN, what is being prioritized, what is being dropped, and also the modem. We can see the stats of the modem. And we can see these things. We have, besides the service, we provide agents. So we have an agent that is monitoring the modem. This is the signal of the modem. This is the azimuth. So one is where the satellite is supposed to be, and the other one is where the antenna is pointing. Because since the vessel is moving, although the satellite keeps the same position, from the satellite you have a relative azimuth and an absolute azimuth. So we have to compare that. And finally we see where it is going so we can monitor all of this. Because we have agents there to know, if suddenly they decide to attack, Jack Sparrow comes here and kills the EMSA guys, we need to know where that happened. So yeah, that's pretty much what we do with EMSA. And if you want to think outside of the box, I recommend you to think outside this box, outside the SD-WAN. Because right now we are combining local ISP with the internet that's coming from the modem. So let's say we want to provide security, but we don't want to use only SES. Somebody said redundancy. We want redundancy for the traffic. Let's say we want to have also Starlink, but we don't want to have 2 PCs. We don't want to have multiple routers. So we use the SD-WAN to combine with Starlink or Intelsat, or with MEO, with SES and Power, in order to provide more security, or we can distribute it via Eagle. So the SD-WAN can do that. And the managed Wi-Fi is because we provide all the way to the Wi-Fi. The service is provided all the way to the Wi-Fi. We can provide only satellite capacity. We can provide internet over satellite. We can provide Wi-Fi. We can manage the Wi-Fi. So if there is something wrong going with the Wi-Fi, they contact us and we remotely fix it. I keep asking them, just pay for our tickets. We will go and fix it on the vessel. But they say, no, you have this link. Please use the link. Budget issues. Anyway, do you have any questions? Do you have any complaints? Please, with Thomas. Do you have any questions? Do you have something you want to ask, something you want to add? Now is the moment. Otherwise, thanks for listening. And I think we're going to be seeing each other in the little thing. There is like a gathering. Are you participating in the hackathon? Who will be in the hackathon? Okay, we have 1. Oh, the rest are not 2. The rest are not coming to the hackathon. Should we invite them? Do they know about the hackathon? Guys, you are invited because Thomas and I will be here. That's enough of a reason. But we're going to be selecting an intern, and we're going to be taking one of the participants all the way back to Luxembourg to show them how we live there with a lot of cows. Thank you very much.
Thank you, René. We are so pleased to have you on our side. But we also have another partner here. With us is our mentor, Carlo Klečina from TIS Grupa. So Carlo will tell a few words about himself and TIS Grupa.
Hi everyone. I don't have a sexy presentation like guys before me. Short about me, I'm a physicist by education. I worked on startups more than 10 years. So when the startup was just a buzzword around here. Today I'm working in TIS Group as project manager. TIS Group mainly works in fintech, supporting financial institutions. We can say that almost every transaction here in Croatia runs through some part of this code. Besides that, we work on artificial intelligence projects. Maybe you heard about Send a few days ago. We launched it publicly and searched a bit, find out how we're helping with help of AI to kids in their development. Thank you. That's all from me.
Thank you so much. And now we'll have a presentation of one of our startups. Mario Špadina from ZICER is with us.
Hvala. Okay, hvala. First of all, morning to everybody. I will not be able to match your enthusiasm in presentation. My blood pressure is a little bit low at the moment. It was a lack of breakfast, but don't worry. So, oh, you know, I am from the coastline. I go a little lower on that. It kind of messes up my articulation. So, thank you for the opportunity to present here. My name is Mario Špadina. I am currently CEO of ZICER, and I hope I will be in coming years as well. And ZICER is a small Croatian startup which is specialized in coastal waters monitoring by high-resolution satellites. Now, listening to the two previous very nice presentations, I would like to give some, for the rest of the audience, some segmentation at least. So, I would say space industry is roughly divided into upstream, midstream, downstream applications, okay, from where upstream would be satellites, hardware, ground segments, and so forth. Midstream would go with data providers a little bit lower to platform providers where all the data are processed, stored, and whatnot, and down to the verticals to the market, which is the so-called downstream satellite provider. We, as a startup, as a Croatia, we are downstream, okay? We take the satellite data, we analyze them, and make value-added services or products. And let's be honest, since it is very young branch of industry, it is all about the same. So I will not go into pitch deck and so on. I will give you a little bit of story where we position ourselves and what is, let's say, European and global trend of this so-called industry. So we are living basically in the funding cycle of European Union devoted to oceans and seas preservation, okay? And of course, it follows a little bit before guidelines of United Nations, where they said, in fact, that we need to take care a little bit of our seas and oceans. Hence, the importance towards the EMSA as well. Now, the problem of pollution, especially in coastal areas, generally, I mean, it causes a little bit of problems, okay? And problems cost money. But roughly, if you don't see what's happening, there is no prevention, there is no mitigation, nor the recovery plans and whatnot. There is no action plans without proper identification of what is happening in coastal waters. When we talk about high seas, they are very nice, for example, in your applications. But there is a thing with high seas. They are infinite reservoir of water. So even if you dump radioactive waste, like La Manche is full of it, okay? Typically, you don't pollute that much because you have infinite reservoir of sea. But things happen, problems happen in coastal waters. And this is why we specialize in value-added services right there. And problems can be roughly divided into two parts. As previous speaker kindly suggested, you can always have so-called dynamic systems of pollution, for example, ships, okay? Cruise ships and whatnot, which can leave both oil spills, fuel discharges, organic pollution from black water tanks, whatnot, okay? You name it, as far as your imagination goes, you can find some sort of pollution. And also, there are static ones, what we call static ones. For example, coastal urbanization. Every village in this beautiful Adriatic Sea is a constant source of organic pollution, to be, let's say, polite. So, but in each case, for example, with EMSA, there is a solution requirement for all types of pollution. Okay, when it comes to seas, lakes, and rivers, I mean, this is a big planet. Not that big in cosmic relations, but big for us, and it's packed with water. So we need some low-cost solutions to monitor. It need to be at least, let's say, frequent, not as a current practices, which has been held in this part of the world. It needs to cover larger areas, and in fact, there are new age requirements that needs to pollute not that much. Greenhouse gas emissions need to be low, and so forth. So the satellite imagery is basically a colossal project by European Union. Is a technology match for those kind of things. Okay, but where we come into play as a CCRAS, oh, I should get this closer, is in fact taking those data and analyze them so that the output data are reliable and higher quality. And this is very important for transparent and near shallow coastal waters, because optical satellites, I will not go into much details unless somebody asks a question, have tendency of not being so reliable, okay? So this is where we specialized in. So, I mean, I will straight go down to the product, because the prototype is operable on a platform provider as a partner, strategic partner. The platform provider, we provide environmental benchmarking, okay? And for the end client, for a partner or whatnot, data on their so-called area of interest. For example, we have here the partner from Zadar Cruise Port, who are very interested, by the way, into seeing, do their cruise ships pollute, okay? They are fighting big negative publicity that they are polluting, but in fact they are claiming that they are not. So what is interesting for them is to see, oh, is something happening or not? So we come into play here, where we divide their entire area of interest, okay? And we scan them by multiple sources of satellite data sources. For example, it can be a SAR data, it can be a radar data, it can be optical data, and whatnot, okay? But what is really important to see is, seas are dynamic systems, okay? They are not, I would say, they are not land. Okay, it's as simple as that. So things happen on the sea on a daily basis, even frequent than that. So you need to always combine satellite data with some sort of atmospheric data, sea currents, maps, wind currents, and so on. Okay, so you really need to see what is happening in perpetuity. So basically, we try to do that in one pot, okay? I mean, there is no other choice. So how do we do it, okay? In a sketch just briefly shown, we combine different satellite data sources. So one cannot really avoid that, because there are enough satellite data providers, but they cost money. So we need to combine first the open source, and then to add some commercial satellite data sources. Okay, so we don't want to spend a lot of money. And of course, all the satellite data, especially in coastal areas, need to be, I would say, calibrated towards what is happening in a real environment. Okay, you need to be sure that the information that you give in the end is reliable. Okay, we don't want to call a national park and say, yeah, you have a big problem over there, make some intervention. And if they don't, and they withdraw tourists from there, it will be a disaster. It will be a disaster for them for one day, but it will be end of career for CCRAS. Okay, so before you go into these kind of things, you really need to make sure. Okay, and of course, after the data processing and interpretation, what we really try to do for end client, client gets a notification, reporting, and of course, transparent visibility of all data on a self-service BI tool, because it's very important. It's like a blood test. You can trust some numbers, but in fact, in a footnote, you have the detailed description, okay, what's happening. So in order for us to be transparent, we give our clients the data, okay? They can visualize it, they can do some things if they want, some certain calculations, but it gives really credibility, okay? And now a little bit about Europe. Europe as being as a complex entity throughout the history, Europe has always new regulations and followed by directives, and then as in fact strategies of the member states. Europe has implemented new directives that really give strict boundaries for not only public institutions but companies as well, that they need in fact to report on the status of what they do. So if you have a hotel in the forest, you will need to take care of the forest, okay? If you have a hotel on the sea, you will need to take care of the sea. So that's quite nice because it gives companies like ours, for the first time, a must-have rather than nice to have. And nice to have is a death for every startup because you don't sell nice to have. So, I mean, we try to do in one package also to satisfy the reporting output, being compliant to both ESG new regulations and EU regulations on preservation of marine environment. Yes, you cannot type it now, but if you type here, if you see the deck, you will be redirected to the web app. Now, we are in blue economy, okay? We are Earth observation company, we deal satellite data, but we are really making a blue economy impact vertical, okay? So typically our clients, so far we have only few, okay? We are an early stage startup. Typically we have national parks, Mljet, Brijuni, Natural Park Telaščica and so forth. ZADR Cruise Port, part of the holding, Global Cruise Holding, I don't know. In fact, it's a big company. But so, you see, we are third-party data provider, okay? But the end client uses its data how they want, okay? Some of them are interested in seeing in long term how is their marine environment, in fact, held or preserved. They will make their action plans accordingly. Some will not. Some will just use it as a PR tool, okay? Say, yeah, we do not pollute, we are happy. Some will use it to say we are better than the other ones. Please come to our hotel resorts because our sea is better. Value proposition for them, we give just an incentive, you use it how you will. But we are third-party quality provider, okay? And it's all transparently visible on the web app. So out of the measurable impact, typically satellites will almost always be near real time, okay? Because they do. It's a trade-off between satellites and I would say IoT. But of course, when you compare the price range about classical sampling methods or giving installations of sensors and so on, typically you always go order of magnitude lower. So that's much cheaper. So that's quite nice. Okay, it's not cheap, but it's much cheaper. And of course, carbon emissions, you don't have you only have a little bit of server hardware emissions, so that's quite nice. Okay, so typically it's a green solution. Nowadays, I have to say it every time because if it's not green, it will not be funded. So it's like that. And yes, just for the market, we are really targeting, you can always go diverse, but we are really targeting maritime transport and energy. Solution that we are, oil spill detection system that we are targeting is EMSA's alternative. I will comment just on that a bit, but it typically follows maritime transport and energy, and of course overlaps with offshore and onshore facilities for typically everything due to energy sector. And we know energy sector is not popular right now, but it's on a high boom because of the crisis with energy due to the war. So it's an opportunity for us, which we hope to leverage. And of course, the coastal tourism. Typically, 50% of money that comes in blue economy is tourism, coastal tourism, okay? And it will not likely to decrease, it will just increase more and more and more, because why? Because people like to go in swimming, okay? And then they eat, and then, yeah, sewage system gets pressurized. So the trend, it's nice that we have colleagues here, because the trend is such that due to the new technology requirements, data providers, platform providers, all the infrastructure that we need basically to make our service in long term shows the decrease in cost. So that's quite nice. And due to the new regulations, basically the client base of the people who need to monitor, or companies or clients that need to monitor and preserve the seas basically is increased. So that's quite nice. It's a momentum that I try to tell to investors. So far not so much, but let's say we are early stage, so I hope they will meet. But in fact, that's an opportunity to grow. Okay, our base, out of our pricing, our base cost goes down rapidly. Okay, with years, because the data providers are competing with themselves, Planet and whatnot. There are a bunch of them. We are in good relations with most, but yeah, we try to strategize there. But yeah, but that's the logic. Okay, we give the small part of what they need to satisfy both the regulations and to invest a little bit more but keeping the costs at minimum. This is the old slide of the team. We have 2 more members. Basically, we have been founded typically in 2020, and we were here one of the ZICER winners, and since then we've grown steadily. But from 2022 we really went much faster, because at the same time you need to decide, do you continue to work on 2 chairs? Okay, typically we were all on the institute, but yeah, the story has grown too large, so we need to pick up the pace here. Question, please. And yes, just for the EMSA. So typically EMSA has a REPAS, and in fact they have a clean CNET. I don't know if your company was responsible in building that. I don't know who it was. I just know the budget because it's a public known figure. So European Agency for EMSA, in fact. I always forget, even though in the correspondence I always forget. So typically they have clean CNET, which is a program that goes for detection of fuel discharges, okay, based on Sentinel-1 data, okay, which is quite nice. It's a nice system. It has 42% chance of detecting something, which is great. Okay, it's a fabulous. But okay, the question arises: is it enough? Okay, and then they have REPAS system, which is unmanned aircrafts. And they are wonderful, okay, but they are location specific, okay. As you kindly guys explained, you cannot just send an unmanned aircraft go around, okay. It costs money and so on, and infrastructurally it's bad to manage. So where we position ourselves, we say there is a gap in terms of land, okay, and in terms of temporal coverage. So you combine, there are already solutions for both combining optical data and SAR data. We position that, so to make temporal segmentation faster, okay, to be, let's say, more real time, but also in terms of hydromorphology of the systems, okay. If you go into coastline, that's problematic, okay. So more you approach to coastline, things get complicated. So we really position ourselves there, okay. So it's unlike, I would say, our tool is like a bridging between true REPAS, okay, in coastal areas, and clean CNET. Now it depends, we'll be recognized as a tool of choice in the upcoming 2 years. So thank you.
Thank you, Mario. Thank you all for coming. And please don't forget to apply to Cassini Hackathon. Application data is until 17th of March. So next live event in Cassini Big Ideas campaign will be held 15th of March here in Accelerator. And please, we can go outside and grab something for it. And